Hi, this is Tzvi Rosen. In today's commutative algebra lecture, we'll be talking about tensor products. First, we'll make some initial definitions and play around with some basic properties of tensor products. Then we'll start to think about the tensor product by a fixed module as a functor from the category of A modules to itself. Then we'll look at exactness properties of that functor. And finally, we'll look at tensor products of algebras. And that'll bring us to the end of the chapter at T. McDonald. Okay, let's start by thinking about tensor product as a quotient. So we're going to look at, we're going to fix A as a ring, and we'll have M and N as A modules. And we're going to define an A module as follows. We're basically going to take A linear combinations. So take A linear combinations of pairs in M cross N. Okay, so just thinking about this set-wise as the direct product of sets M by N, and we're taking A linear combinations. You can scale any one of these pairs by an element from the ring, just by kind of formally attaching that element of A to that pair. You can also add them together arbitrarily. So typical element will be sum of AI MINI, where I will range over some finite index set. This is called the free module on M cross N because you can take free A linear combinations. So this is denoted A to the M cross N. Okay. Now we're going to introduce a submodule. So let D be the submodule of this free module. Generated by, so we're going to have relations of the following type in this submodule. We're going to have AI times MINI. Actually, we can forget the indexes. Just make it AMN will be set equal to AMN. Similarly, the same relation will hold by passing in to the second factor. Right? So now we're saying that you can scale in either one of the two factors, and it will amount to the same thing. Okay, and the reason I'm denoting this as differences is because once we quotient out by this submodule, these two elements will be considered equal, since they're differences in the submodule. Okay. Next, we're going to have linearity in each factor. So we want to have M1 plus M2 N will be equal to the sum of the two pairs separately, M1N, M2N. Okay, so you can add the two pairs, and you can combine them in the first factor. This will be number 3. You can do the same thing in the second factor. So if you have M N1 plus N2, this will be set equal to M N1 plus M N2. And when we quotient out by D, so if we take A So we're going to define this to be M tensor n. This is going to be defined as the quotient of the free module by the submodule generated by all of the differences that we just mentioned. And so for an arbitrary element in M tensor n, so for any xy in, so if once we start in this module, so we pass the image in M tensor n after quotienting out by d is written as x tensor y. And we have the following properties just based on definitions of definition of D, that ax tensor y is equal to x tensor ay, and it's equal to a times both. And then you also have the additivity in each factor. Okay, so we're able to engineer this special object which has this alinearity in each factor by just forcing it to have that alinearity, and that's what we've done so far. Okay, so that's how you define the tensor product as a quotient. You can also define it in terms of a universal property, and you've spoken a little bit about this in some of our problem sessions, how to define an object by a universal property. But here's the diagram associated to the tensor product. So for M and N A modules, there exists an A module called M tensor n and a map, say it's an A bilinear map G from M cross n to M tensor n with the following property. That given any A module P with an A bilinear map F from M cross n to P, it's going to factor through the tensor product in a unique way. Okay, so for any A module P and A bilinear map, and again, A bilinear just means it has the linearity properties we mentioned already. It scales with A, and you can add. So for any A module P and A bilinear map F, let's put that here, F from M cross n to P, there is a unique map F prime from the tensor product to P, and it'll be an A module homomorphism. Let me write that, A module homomorphism, such that F prime composed with G is going to be equal to F. Okay? And so now that we know that such a thing exists, all right, and you can it's not hard to to show that this property is satisfied by the object that we just described, that the quotient of the free module by that submodule with all the linearity relations. Once you show that it exists, you also show that it's unique, because if you have, okay, suppose there are two such. Suppose m square n satisfies the same property. Well, then that means that I can put m square n here, or I can copy this diagram, put m square n here and m tensor n here, and this tells me that, okay, so let's say there's a g prime for m square n. So this diagram tells me that each of these forces a unique morphism here, a unique a-module homomorphism here. Okay, so the property forces a unique a-module isomorphism. Okay, based on this unique map, going first this way and then this way. So from m tensor n to m square n, and then back to m tensor n. Okay, so the fact that we're using two factors here is convenient, but it's not forced in any way. You could do it just the same way with multiple factors. You'll just need a larger, when you're proving the existence of this module, you need to quotient out by more relations. So let's describe the differences. So first of all, it needs to be alinear in each factor. That means that in the corresponding existence proof, the free module and its submodule look different. But otherwise, because you have this neat property, this universal property, which characterizes it pretty nicely, the rest of it carries through in the same way. Now we'll cover some quick isomorphisms from the text. These are listed in proposition 214. And the isomorphisms are as follows. If you have m tensor n, for instance, an element there would be x tensor y. That's isomorphic to n tensor m under the map, just reversing the order. If you have three a modules, mn and p, then you get this three-way isomorphism, which is kind of like an associative property. So here you could put the parentheses anywhere you like. Okay, as for this direct sum, take x and y, pair of elements defining an element of the direct sum, tensor with p, tensor with z, let's say, an element of p. That gets mapped to x tensor z, y tensor z. As for a tensor m, if you have an element of the ring, tensor something in the module, then you just send that to the product. Okay, since the module has an a multiplication endowed to it. Okay, so how do we show that these are actually isomorphisms? for most of it, we just want to use the universal property. So at every point, we assert the existence of some bilinear map or multilinear map, and then we show that that implies the existence of a unique homomorphism, which helps us get to isomorphism. So let's explore how this applies in this isomorphism. If we take the tensor product of n and p, and then tensor with m, that equals the three-way tensor product of m, n, and p. And so in order to do this, we're going to show the existence of two maps. First, the map going this way, and then the map going this way, and then assert that composition gives you the identity, which implies isomorphism. We're going to start by fixing an x in M. Okay. And we're going to define the map from n cross p. So take fx from n cross p and map that to m tensor n tensor p, sending yz to x tensor y tensor z. Okay, here y and z can be any elements in n and p, but x is fixed. All right, it's indexed by the map. So it's not hard to tell that this is linear in both coordinates. This is a bilinear. So that means that there's a unique map from the tensor product n tensor p to the same module. Okay? So great. So now we have a map from the tensor product for each element in M. But now we can consider mapping. So let's map f from M cross n tensor p to m tensor n tensor p by taking, so for a fixed x and a fixed t, we'll just map that to fx prime of t, right? Because fx prime maps n tensor p to m tensor n tensor p, and so this is perfectly well defined. And we also note that this is a bilinear in both coordinates. Rather, it's alinear in both coordinates. It's a bilinear. And so that implies, by the same universal property, that there is a unique f prime mapping m tensor n tensor p to m tensor n tensor p, which agrees with the maps we've described so far, i.e. it sends x tensor y tensor z to x tensor y tensor z. Okay, and going in the other direction for G, it's a little easier. So you have m cross n cross p maps to m tensor, let me resize this a bit. Okay, so if we take the map sending m cross n cross p to m tensor n tensor p, to m tensor n tensor p, which sends x, y, z to x tensor y tensor z, it's plain to see that this is alinear in every coordinate. or a trilinear in this case. So that implies we have a unique homomorphism. Let's call this G. So there's a unique G prime from the three-way tensor product. Okay, and in terms of how we know that that the composition of these two gives you the identity, well, just by definition of how that map acts on the elements of each module, we can identify that it acts as the identity. Okay, so that's how you would show it for one of these examples. We could also show it for direct sum, but perhaps we'll leave that as an exercise. Okay, now let's think about restriction and extension of scalars. So we spoke about this a little bit when we were first exploring rings, and we talked about contracting ideals and extending ideals. So let's give ourselves a similar setup. So suppose we have rings A and B, and we have a homomorphism F from A to B. Okay, so there are two scenarios we could have with the module. Either it's in the and as in that earlier discussion, we're going to pretend that A is the smaller ring and B is the larger ring. So when we start in A, we extend to B, or when we start in B, we restrict to A. We're going to start by fixing an X in M. Okay, and we're going to define the map from N cross P. So take Fx from N cross P and map that to M tensor N tensor P, sending YZ to X tensor Y tensor Z. Okay, here y and z can be any elements in N and P, but X is fixed. All right, it's indexed by the map. So it's not hard to tell that this is linear in both coordinates. This is A bilinear. So that means that there is a unique map from the tensor product N tensor P to the same module. Okay, so great. So now we have a map from the tensor product for each element in M. But now we can consider mapping. So let's map F from M cross N tensor P to M tensor N tensor P by taking, so for a fixed X and a fixed T, we'll just map that to Fx prime of T, right? Because Fx prime maps N tensor P to M tensor N tensor P. And so this is perfectly well defined. And we also note that this is a bilinear in both coordinates. Rather, it's alinear in both coordinates. It's a bilinear. And so that implies, by the same universal property, that there is a unique F prime mapping M tensor N tensor P to M tensor N tensor P, which agrees with the maps we've described so far, i.e. it sends x tensor y tensor z to x tensor y tensor z. Okay, and going in the other direction for G, it's a little easier. So you have m cross n cross p maps to m tensor, let me resize this a bit. Okay, so if we take the map sending m cross n cross p to m tensor n tensor p, to m tensor n tensor p, which sends x, y, z to x tensor y tensor z, it's plain to see that this is alinear in every coordinate, or a trilinear in this case. So that implies we have a unique homomorphism. Let's call this G. So there's a unique G prime from the three-way tensor product. Okay, and in terms of how we know that that the composition of these two gives you the identity, well, just by definition of how that map acts on the elements of each module, we can identify that it acts as the identity. Okay, so that's how you would show it for one of these examples. We could also show it for direct sum, but perhaps we'll leave that as an exercise. Okay, now let's think about restriction and extension of scalars. So we spoke about this a little bit when we were first exploring rings, and we talked about contracting ideals and extending ideals. So let's give ourselves a similar setup. So suppose we have rings A and B, and we have a homomorphism F from A to B. Okay, so there are two scenarios we could have with the module. Either it's in the and as in that earlier discussion, we're going to pretend that A is the smaller ring and B is the larger ring. So when we start in A, we extend to B, or when we start in B, we restrict to A. Okay, if M is a B module, it's not hard at all to give it the structure of an A module, so we just need a way to multiply elements of A. So it has an A module structure. And you define the A multiplication simply as B multiplication, but you just pass to B first. Okay, because if X, so for A in A and X in M. Okay. If, on the other hand, M is an A module, it's a bit more complicated because we don't really have a way to multiply by most things in B. But what we can do is just make sure that it's interacting well over the things we can multiply by. So we take B tensor product with A of M. Tensor product over A with M. And now this has a B module structure. has a B module structure. Because if you multiply any element of B here, so B tensor over A with X, let's give it a B prime here, you can just multiply in the first coordinate. But we still have the ability to scale the second coordinate by A, by elements of the ring A. Okay? In particular, we would have B tensor AX would be equal to AB tensor X, which is, we would define as f of A times B tensor X. Okay? Because we want the multiplication to happen in B. Okay, and these two module structures tend to have nice things in common, like finite generation as one type of module gives you finite generation as the other type of module. And you can see this in a T.M. McDonald for more detail. Okay, and now we move to functor land. Okay, so you'll recall from previous talks that we have A modules as a category, with A module homomorphisms as morphisms of the category. And now I'm going to claim that for fixed M, so fix in A module M, then this map, which takes for any module, so on objects, you take N, an A module, and it maps you to N tensor over A with M, and this is also an A module, right? Because we can scale these elements in either coordinate, giving the same thing. Okay, how about the morphisms? So given an A module homomorphism F from N to P, we're going to map N tensor M to P tensor M, and this is just going to take so N tensor M, and it's going to map it to F of N tensor M. Okay, so in other words, you're basically taking, so this should be, let's call this F prime. In other words, F prime is essentially F in the first coordinate and the identity map in the other coordinate. Okay? And this is a functor. This is a functor from the category to itself. And like the hom functor, we're going to want to explore some of its properties. And before we do that, we're going to give a quasi-definition. Again, I apologize for kind of the shakiness of a lot of these definitions. I don't want to do a full category theory unit, but I still think kind of the general notions of category theory are very useful here. So a quasi-definition of an adjoint functor is it's kind of like an inverse functor. So if you have a functor f from a category C to a category D, and a functor g, which takes you from the category D to the category C. So if we take an object x in category C, so in the objects of C, and an object y in category D, then we have the following bijection. So if the maps or morphisms, sometimes use hom, sometimes morphisms, of x to gy. Okay, now this is taking place in category C because G maps y to C. This is in bijection to the homomorphisms in D of f of x to y. Okay, so the maps between x and g of y in category C is in bijection with maps from f of x to object y in category D. Okay, so yeah, and this has to be in a particular way. So in a natural way, and that involves describing this hom business as a functor to sets. Okay. Now the key here is that the tensor product with M for a fixed M and homomorphisms from M to any module, so for the same fixed M, these are adjoint functors on the category of A modules. Okay, so given N and P in category of A modules, we want to show that there's this natural bijection between, on the one hand, hom of n tensor M to P, and on the other hand, hom of M to hom M. Sorry, this should be hom of N to hom MP. Okay, so I should be able to take any map F in here. So given F in that maps n tensor M to P, an A module homomorphism, this should naturally go to some F prime, which maps N to another map from M to P. Okay. So let's consider how this would work. So you'll notice that this A module homomorphism from n tensor M to P, if we fix a particular n in N, so fix n in N, then what results is just a map which is linear in M from M to P. So that's just an A module homomorphism from M to P. Then what results is Fn mapping M to P. So this A module homomorphism F from n tensor M to P, when we fix a particular element of N, that gives us a map from M to P, much as we need. So, but how about going the other way? So given something here, how would we go here? And the way you would do that would be to define f of n tensor M as simply f prime of n, then apply, sorry, it should be, f prime of n, so that's a map from n to the homomorphisms from M to P. and then apply that homomorphism to M. So this should give you, this should be in P. Okay, so that's a way to define f on this tensor product, and by checking A module homomorphisms that everything lines up, this is indeed a valid way to translate back, and these two correspondences compose to give you the identity. Now we've established this is a functor from the category of A modules to itself. And the fact that it's a left adjoint to hom, or in general that it's just a left adjoint, so since this functor is a left adjoint in the way that we've described above, it is a right exact functor, which means that, more specifically, if you have a sequence of modules which is exact, then applying the functor to each step of the module will remain exact. Okay, and it's called right exact because this is true for this side of a short exact sequence, but it's not true for that initial step from 0 to n prime. Another way of saying this is that this preserves co-kernels. And you'll recall that hom was left exact because it was a right adjoint to tensor. So it's this is one of the special properties of adjunction, is that you pick up this nice exactness property. In terms of proving this property, so you could say, oops, so if we start with n prime mapping to n double prime mapping to 0 being exact, so if we start with this top sequence exact, well then by exactness of, or by left exactness of hom, I can write hom of n double prime p to hom np to hom n prime p. Oh, and I should have a 0 in front here. So this will also be exact. But it doesn't really matter what p is here, what module p this is. So we can pretend that it is itself a hom module. So we have a hom of n double prime to hom of m, and now let's make it p prime because this is a new module, and then we can map that to hom of n to hom of m p prime. Here I'm just setting what p is. I'm not doing anything fancy. To hom of n prime hom m p prime. This is also exact. But then I know that I can use the adjunction properties here. So I know that hom of a given module to a hom is equal to a hom from a fixed n is equal to the same thing as the hom of M tensor, that first module, to P prime. So this implies that 0 to hom of M tensor, and we'll use the commutativity to put M afterwards, n double prime tensor M to P prime. Oh, sorry, I'm still using tensor. Tensor M P prime to hom of n prime tensor M to P prime. This is also exact. And then when you have a sequence of homs being exact, that implies that the original sequence was exact to start with. Okay? So that's the logic to show that this tensor product sequence is in fact exact. So that tensor is a right exact functor. You can derive, using a similar counterexample as we found with hom, that tensor with M is not a left exact functor as follows, even though it is a right exact functor. So we're going to take A to be Z, and now we're in the category of Z modules. So the category of Z modules. And we're going to take the following exact sequence. We have 0 maps to Z, maps to Z, maps to Z mod 2Z, maps to 0. So the map here is going to be the multiplication by 2 map. Now consider what happens when we tensor over Z with Z mod 2Z. Okay, so this sequence becomes 0, Z tensor Z2, I'm going to abbreviate Z mod 2Z as Z2, Z tensor Z2, Z2 tensor Z2 maps to 0. Okay, and this second map now becomes multiplication by 2 in the first coordinate, and then just the identity in the second coordinate. Okay, and that's how this functor works. But we'll notice that now, at this stage, the functor is not exact. The sequence is not exact, because the image of that first map, 0 to Z tensor Z2, is obviously just the 0 submodule, but the kernel of the next map, kernel of Z tensor Z2 to Z tensor Z2, this is going to be the entire module, because when we do this multiplication by 2 in the first coordinate, so n tensor x mapping to 2n tensor x, well, that's equivalent to n tensor 2x, which is equivalent to 0, because 2x in Z2 is always 0. So that means that everything is in the kernel of that map, but this module is not the 0 module. So these two things are not equal to each other, which means the sequence is not exact.